Intermolecular forces greatly influence the properties of liquids. Okay, so our chemical properties are going to be influenced by these intermolecular forces. So how do we deal with our solubility, viscosity, surface tension, vapor pressure, boiling point? Okay. When we look at solubility, our rule for solubility is like dissolves like. And so intermolecular forces come into play here because if I have similar intermolecular forces, stuff will interact, we'll get stuff to dissolve in each other. If I do not have similar intermolecular forces, then things won't dissolve because I have my solvent molecules and I have my solute particles. And so if I don't have good compatibility between the solvent and solute, I won't be able to replace the solvent-solvent or solute-solute interactions with solvent-solute interactions. This is why oil and water don't mix. Oil is a long straight chain hydrocarbon with only dispersion forces. It's nonpolar. Hydrogen's this small little highly polar hydrogen bonded species, and so those two don't mix very well with each other, and so they separate. They don't play well, they don't want to mix, so we don't get the solubility there. When I look at this picture right here, okay, I have ethanol in water. Ethanol has a 2-carbon side chain, and it's got an OH end on the end of it, so it's still small. Okay, the 2-carbon side chain doesn't get terribly in the way of reaching that little polar head that is polar and can hydrogen bond. And so we do get that mixing between our methanol and our water. Okay, viscosity, again, resistance to flow. So if something has strong intermolecular attractions, they're not going to flow past each other very easily. They're going to stick more and not want to flow. And so the stronger the intermolecular forces, the higher the viscosity, the more resistance we have to the flow. Viscosity does decrease with heating. So if we heat something up, we can lower the viscosity. So this is why, like, oil in your car, it's important because you may think like, well, it's really thick. Well, it's thick when you're pouring it in when it's cold, but when your car's running, it's a lot hotter, and so that oil thins out quite a bit because we have much lower viscosity when we heat things up. Okay, so here's an example here. I've got fluid A and fluid B. Okay, so which fluid has the higher viscosity? Fluid A does, because it's the one that's not flowing very well at all. In fact, fluid A is at an even steeper angle than fluid B is, and it still doesn't want to pour. So A has a higher viscosity than B does. Okay, again, when we look at that viscosity of water, when we are heating it, if I look at water at 20 degrees Celsius compared to 80 degrees Celsius, you can see that the viscosity is a whole order of magnitude smaller for my 80 degrees than my 20 degrees. So you heat stuff up, the viscosity goes down. All right, our surface tension. So we've got all these intermolecular forces. So in the interior, a molecule is going to be attracted on all sides to everything. But on the top, on the surface, now there's no similar particles above it. So it's being attracted downward by the particles below it and to the sides of it. So it'll move into the interior. Things get more stable because now I have equivalent interactions on all sides. And so our liquids, they tend to have the smallest surface area possible because they're trying to minimize and stabilize everything so everything is covered by all the intermolecular forces as much as possible. So we have two things going on. We have adhesion and cohesion. Okay, so adhesion, we bind to a surface. Cohesion, we bind to itself. So liquid mercury has really high cohesion because it doesn't really interact with the containers that it's put in. And so liquid mercury balls up because it's more strongly attracted to itself than it is to anything around it. Okay, and so you can see our mercury here has the highest surface tension. Well, because what's holding it together? A metallic bond, not an intermolecular force. So bonds are intramolecular forces, and that's what actually puts individual molecules or things like samples of metal or ionic bonds that hold ionic compounds together. Okay, water has the next highest surface tension with its very strong hydrogen bonds. Okay, so the stronger the intermolecular force, then the stronger that surface tension is going to be. Okay, and then the surface tension of water, you can get stuff to interact with the surface of water. You can sometimes get paper clips to float on water if you have a big enough vessel and it's deep enough that can handle that disruption on the surface. Water bugs actually have things on their feet that interact with water molecules, which is why they're able to walk on water. They're spread out, and then again, they've got these things that interact on the surface of water that prevent them from sinking in. Okay, and so when we look at our adhesive and cohesive forces, well, water has adhesive forces to our glass because our glass has silicon dioxide that it's made out of. And so we can get hydrogen bonds between the hydrogens on the water and the oxygens in the silicon dioxide. So that's why we see the meniscus that we see. So you can see up here, I've got this little picture there of that meniscus. So our surface tension is the water molecules interacting with each other, and then I've got the adhesive forces where it's interacting with the test tube. Mercury, though, because it's more strongly attracted to itself, instead of going up the test tube, it pulls away from the test tube. And so instead of getting a meniscus that is like this, we get something that looks like that instead, because the mercury is pulling away from the sides. Okay. Capillary action, because we have that interaction between water and our glass. Anything else that's got that attraction, we get this capillary action where we get those interactions, and so it crawls up the side of the tube. Okay. I actually had a really bizarro example of this when I was younger. I had this craft kit that had these little dye pouches. I didn't finish what I was working on, and the dye pouches didn't reseal. So I sat the dye patches in a plastic bag straight up, and then I taped the plastic bag to my wall so that the dye wouldn't leak out. Well, the dye interacted with the sides of the pouch that it was in, and after a few days, I could see dye leaking out of the top of the pouch, even though the pouch was standing straight up. And so, being the curious about everything person that I am, I let it sit. And after a time, I had stuff pooling in the bottom of the bag. And then I had stuff climbing up the side of the bag because there were interactions between the dye and the plastic in the bag. So my art project ended up being turned into a science project as I watched the capillary action slowly draw my dye up the side of this bag until it started leaking out at the top of the bag, and I finally had to take it down so that I didn't make a mess. So capillary action is pretty cool. All right, our vapor pressure. Okay, so this is the pressure exerted by a vapor that's in equilibrium with the vapor or the liquid phase. And so as we start to go from the liquid to the gas, we build up our vapor. And so at lower temperatures, below the boiling point, we're going to have less vapor. And as we get closer to the boiling point of something, we're going to have more vapor. And so our intermolecular forces, that's what's holding these things together. And so if I don't have very strong intermolecular forces, it's not going to take much energy to enter the vapor phase. So I'm going to have a higher vapor pressure with lower intermolecular forces because I have more molecules easily entering the vapor phase. And so you can see that here, okay? Ether has a much lower boiling point than water does. And so at 35 degrees Celsius, I have a lot more molecules in the vapor phase for ether than I do for water. Higher vapor pressure, lower intermolecular forces. Okay, so you can see that there. All right, and there's a graph if you like that better, right? And so lower temperature, higher vapor pressure for things that have lower intermolecular forces. Okay. All right, and then boiling point, this is where our vapor pressure equals the external pressure, which is the atmosphere typically. And so boiling point is going to depend on that applied pressure. So the more pressure I have pushing down on it, the harder it is for that stuff to escape into the vapor phase. So this is why when you try to boil things at high altitude, they are going to boil at a different temperature, because at high altitude you have lower external pressure. And so it's easier for things to enter into the vapor phase. And so your boiling points go down when you're at higher altitude. My aunt moved from San Diego to a mountain town up near Yosemite when I was younger, very high altitude. And I remember her saying how it took her time when she first moved up there to learn how to cook on a regular basis at high altitudes, because it changed these sorts of things. So lower external pressure, we need less kinetic energy to form these bubbles, and so we're able to vaporize easier. All right, when I look at boiling points, okay, heat of fusion means the heat or the amount of energy required to go from a solid to a liquid, and heat of vaporization is the amount of energy required to go from a liquid to a gas. All right, and so the stronger our intermolecular forces, the higher those heats of vaporization are. Okay, and so again, stronger intermolecular forces, higher boiling point. Now, when we look at water, okay, if we were to look at trends on the periodic table, if we were to look at group 6A and look at the other hydrogen containing compounds in group 6A, okay, we get a trend. And then we get to water. And water doesn't follow the trend. Water, we actually see a boiling point significantly higher than we would expect because of the way water hydrogen bonds. So we also see that with ammonia, with water, and hydrogen fluoride, because all three of these hydrogen bond. So we can actually plot it, and you can see the other hydrogen containing compounds of group 4A, 5A, 6A, and 7A, and how they all follow trends pretty much until you get to our hydrogen bonders, and they have significantly higher boiling points than we would have expected because of the hydrogen bonds. Water, we have the sharpest increase in the boiling point because water can form 4 simultaneous hydrogen bonds. Okay, and this dotted line here, this is extrapolated where we would have expected the boiling point of water to be. So very close to negative 100, but what do we know? Water boils at 100 degrees Celsius. So water, because we have 2 lone pairs and 2 hydrogens, I can get 4 simultaneous hydrogen bonds across the entire sample of water. With hydrogen fluoride and ammonia, I don't have that evenness. So water looks like this. Okay, hydrogen fluoride looks like this, and ammonia looks like that. And so hydrogen fluoride, I have 1 hydrogen and 3 lone pairs. Ammonia, I have 1 lone pair and 3 hydrogens. And so I can't get 4 simultaneous hydrogen bonds across the whole sample because I have an uneven number of hydrogens and lone pairs. But water, though, I do have an even number of hydrogens and lone pairs. And so water holds together really strongly, and it makes water really hard to break apart. And so we see a lot of really unique things with water because of these hydrogen bonds. Water does not follow what we would have expected it to follow if we look at trends of other similar compounds like it. These hydrogen bonds are responsible for a lot of what water does and why it does what it does.